In this video, we will be looking at chemical systems at equilibrium and the equilibrium law. From what we've already learnt, for a system to be at equilibrium, it must have a closed container and it must be at a constant temperature. If you don't meet these two criteria, the system cannot reach equilibrium. Now, once a system is at equilibrium, it is characterized by the rate of the forward reaction equaling the rate of the reverse reaction and constant macroscopic properties. Remember, macroscopic properties are anything you can see, such as color, or anything you can measure, such as concentrations, pressures. Now let's look at a hypothetical system. We have reactants which are called A, and we have products which are called B. When A reacts to form B, this is considered to be the forward reaction. When B reacts to form A, this is considered to be the reverse reaction. It is usually written as A with an equilibrium arrow. You can see the equal sign in the arrow, which has two barbs on the end to show the forward and the reverse reaction. Now let's consider our A and B equilibrium system. The reactants are represented by A and the products are represented by B. At time equals 0, you can see we have a high concentration of reactants A. Now, concentration can be represented by square brackets. As time is going on, as A is beginning to form B, the concentration of A decreases. Now, because B is forming, the concentration of B increases until the system reaches equilibrium. Now, equilibrium, remember, is characterized by constant macroscopic properties. And you can see here that our concentrations are constant, so they're the same. So the concentration of A remains the same and the concentration of B remains the same. So their concentrations are constant. So this is telling us that we have reached equilibrium. Now you must remember this is a dynamic equilibrium. That means that the reactions are still taking place, but they are taking place at equal rates. So the A forming B is occurring at exactly the same rate as B forming A. Now let's look at the rates of reactions for our system of A forming B and B forming A. Remember, we initially started with a high concentration of A. So we had a very high concentration of A. And we had 0 concentration of B. Now, you need to revise collision theory here. If you have a high concentration of A, that means that you have a greater number of total collisions. This means that you increase the rate of reaction because of a greater number of collisions. Because B had 0 at the beginning, its rate of reaction was also 0. Now, as time is going on, you can see that the concentration of A is decreasing. Now, if the concentration of A is decreasing, this means there are less collisions, which means you have a lower rate of reaction. And you can see this in this diagram. What you're seeing here, though, for B is as the concentration increases, you increase the total number of collisions, which means you increase the rate of reaction. Now, eventually they reach equilibrium. Now remember, equilibrium is characterized by the rate of the forward reaction equaling the rate of the reverse reaction. Now, equilibrium law. Chemists have found that once a system has reached equilibrium, there is a quantitative relationship between the concentrations of the reactants and the products. So let's consider this reaction. So these are our reactants and these are our products. Now the relationship is in comparison of the products to the reactants, and they've found that the concentration of C to the coefficient of C multiplied by the concentration of D to the coefficient of D divided by the concentration of A to the coefficient of A times the concentration of B to the coefficient of B. Now this here is called an equilibrium expression, and it can be used to quantitatively work out the equilibrium constant. And the equilibrium constant is a number. So for this particular example, if you had a greater proportion of products, then your Kc is greater than 1. If you have a large proportion of product. If you have a large proportion of reactants, then your Kc will be less than 1, which means that you have large proportion of reactants. I've put a link to a video here that you might want to watch. Now, characteristics of the equilibrium constant. Remember, it is a mathematical relationship between the concentration of products to reactants. Each equilibrium system has its own equilibrium constant, and it's temperature dependent. So you change the temperature, you change the proportion of the reactants and products, then you change the equilibrium constant. So this is really, really important to remember, that it is temperature dependent. Now, solids and liquids are not included because their concentration is constant. Think of the kinetic theory of solids and liquids. Their particles are already extremely close together. We cannot get them any closer, so we give them the constant value of 1. It doesn't provide any information about a rate of reaction, but it does tell us the proportion of the reactants to the products. So remember, if your Kc is greater than 1, your products are favoured. If your Kc is less than 1, the reactants are favoured. In your course, you are expected to be able to interpret the mathematical number of an equilibrium constant, and you are expected to be able to write an equilibrium expression. This equilibrium expression question will turn up in every WACE exam, so it's important that you can do this. So let's go through. K. Kc means equilibrium constant. Kp would mean equilibrium pressures. Ksp, equilibrium solubility products. So they just have slight variations. Kc is fairly generalized. Now, we start with the products. So we want the concentration of HCl. Now we know that it's included because it's a gas and its concentrations can vary. Remember, do not include solids or liquids because their concentrations are constant. Now, It has a coefficient of 2, which means that you square its concentration. It's divided by the concentration of hydrogen multiplied by the concentration of chlorine, and their coefficients are 1, and hence that's what it is. Now let's look at this example. Remember, do not include solids or liquids because they have constant concentration. So the equilibrium expression here would be, we've got gas, gas and solid. The concentration of ammonia multiplied by the concentration of hydrogen sulfide and divided by 1 because this one's concentration is constant. So NH3 by H2S is the equilibrium constant. Your task is to complete the questions on OneNote and STAWA Set 5.